Welcome back. This is part 2 of 4.2 water. This is our first science understanding. Desalination is a process used to remove minerals from saline water to produce fresh potable water. Reverse osmosis and thermal distillation are two widely used methods for desalination. We'll also need to be able to describe the disadvantages of using desalination for the production of potable water. This is a picture of the Adelaide desalination plant, which is located in Lonsdale. This was fairly recently built, so back in 2012, and it was built in response to a pretty bad period of drought that South Australia suffered. So desalination is a process that is used to remove dissolved salts and minerals from saline or seawater. This then results in potable water, and potable water essentially means it's safe for human consumption, but also human use. This can be achieved through one of two ways. It can be thermal distillation or reverse osmosis. Thermal distillation is a process which is a bit more common in the Middle East. This is because rainfall is quite low there, and they do have a fairly high abundance of fossil fuels which they can use in this process. Essentially how this works is that seawater is fed through pipes and it is heated. That heat could be produced by the combustion of fossil fuels. The water then evaporates and eventually it will condense and cool into collection vessels. So here we can see the evaporation and then condensation of water into these collection vessels. And the water essentially is isolated as pure water. One of the concerns is at the bottom, we can see that there is a buildup of a concentrated salt solution which we call brine. And this is usually safely returned back into the sea through a series of diffusers to ensure that we aren't severely affecting the concentration of the seawater. The second method of desalination is through the use of reverse osmosis. We can see that in this diagram here in step 4. What this shows you is that seawater typically undergoes a series of processes before we can carry out reverse osmosis. So for example, we have intake screens which attempt to prevent any intake of marine life. We have flotation units which can allow for the coagulation and flocculation of clay particles and other components. And also in step 3, a gravity sand unit which is essentially designed for filtration. This leads into the next science understanding. Reverse osmosis is a filtration technique whereby water is forced under pressure through a semi-permeable membrane. You'll need to be able to explain how reverse osmosis produces potable water from saline water. Before we can talk about reverse osmosis, we need to talk about what osmosis is. To understand the process of osmosis, what we can see on the left here is a tube which consists of water. In between, we have this so-called semi-permeable membrane. To the left, we have water with a low concentration of a salt, and to the right we've got water with a high concentration of salt. This semi-permeable membrane allows for small molecules like water to flow through it. However, it doesn't allow for these components dissolved within the salt to do the same thing. What we know is that water will typically flow from an area where it is more concentrated, or another way of saying that is that there is a lower concentration of a solute contained within it, to a region where there is a lower concentration of water, or again in other words, a region where there is a higher concentration of solute particles. This flow of water from low solute concentration to high solute concentration has to take place through a semi-permeable membrane. And what it's trying to do is essentially equalize these concentrations on the left and right side. So overall, we will see the movement of water from the left to the right through the semi-permeable membrane until it equalizes the concentration on both sides. One other thing to factor in is that osmosis is a passive process. So what that means is it doesn't require energy input to do so. Water essentially naturally flows from low solute concentration to high solute concentration. As you can imagine, reverse osmosis is essentially going to be the reverse. Here we can see one side with a low solute concentration, on this side water with a high solute concentration, so we can think of seawater. What we're trying to do is remove the water from this seawater and end up with a highly concentrated brine solution. To do that, we have to force water to flow in the opposite direction. So in other words, we want it to flow against its natural tendencies. To do that, we would need to supply external pressure, which can be quite energy intensive, to get water to move from an area of high solute concentration to a region of low solute concentration. As a result, on the left side, we will end up with fresh water without this high concentration of salts. However, the seawater itself, like mentioned before, will become very, very concentrated. And like with thermal distillation, we would look at needing to find a way to dispose of this. So typically this is dispersed back into the ocean and into the seas through a series of diffusers to try and safely remove it without significantly affecting the salt concentrations in the sea or ocean water. Reverse osmosis is essentially how the Adelaide desalination plant acts to treat seawater. The construction of the desalination plant was relatively controversial, and that's because the desalination plants themselves have advantages as well as disadvantages. If we look at the advantages first, we know that they can produce potable water. It also reduces the demands on fresh water. Another benefit is that it's not dependent on climate, so things such as rainfall. And it does end up producing a reliable source of fresh water or potable water. Some downsides, however, is that they can be extremely energy intensive processes. They can be expensive to produce and to maintain. The waste products and the heat disposal may be an environmental concern, and at times the water inlets can even drag in and kill marine life, so it's not good for the local ecosystems. This is our last science understanding. Hypochlorous acid, chlorine and hypochlorites are oxidizers used for water disinfection. Explain the effect of pH on the equilibrium between chlorine and water and hydrochloric acid and hypochlorous acid. Water disinfection is one of the last steps in producing potable water. This typically involves the use of chlorine and its associated compounds, such as chloramine, and these are used to help disinfect our water supplies. One way to do this is to inject chlorine gas into water. The chlorine gas reacts with water and it establishes an equilibrium. That's shown by this equilibrium process here. Over to the right, we can see the formation of two key products. This one's been broken up into two components. We have hypochlorous acid, HOCl, and hydrochloric acid being expressed as H plus and Cl minus. That's because hydrochloric acid is a strong acid which readily ionizes, or we can think of it as readily dissociating to produce ions. Another way of looking at this is to show how chlorine reacts with water to produce hydronium ions instead of hydrogen ions, which we know actually don't exist independently in solution. So either or equation can be used to show this equilibrium process. It's important to note that this equilibrium process is going to be pH dependent. So we're going to firstly consider this reaction, and we're going to look at what happens when the pH is decreased or increased, or in other words, at low pH and high pH. We'll start off with low pH. If we were to decrease the pH, what that essentially means is that we're going to increase the concentration of hydronium ions in solution. Because it's an equilibrium process, we know that the equilibrium system will want to offset this increase in concentration by trying to decrease it. And to do that, we would see that the equilibrium will favor the back reaction, or in other words, the equilibrium will shift to the left. So that means that more of our products on this side are going to form into chlorine gas and water. As a result, this increases the concentration of chlorine gas, which is actually an undesirable thing. On the other hand, if we were to increase the pH, what this will do is increase the concentration of hydroxide ions, and we know that this can react with hydronium to produce water, and in doing so will decrease the concentration of hydronium ions. So the system itself is going to then favor the forward reaction to try and increase it again, or in other words, the equilibrium is going to shift to the right. and in doing so this is going to increase the concentration of hypochlorous acid as well as hydrochloric acid. However, it's worth noting that hypochlorous acid is our substance of focus. This is the key disinfecting agent, and I'll explain why later. As I mentioned before, hydrochloric acid is a strong acid, so that makes hypochlorous acid a weak acid. And we know that hypochlorous acid, it is a molecular structure, but it has the ability to act as an acid and to lose protons. So in the presence of water, it can essentially undergo ionization to produce what we call hypochlorite ions. That can be represented in this equation here, and you can note that this is also an equilibrium process. So HOCl reacts with water, it produces hypochlorite ions as well as hydronium ions. Like with the previous equation, this equilibrium is also going to be dependent on the pH. So we can consider what would happen if we were to decrease or increase the pH. Starting off with a reduced pH, so again we know this will increase the concentration of H3O+ on this side here. So the equilibrium we can expect will shift to the left, and we will end up with an increase in the concentration of HOCl and a decrease in the concentration of ClO-. For increased pHs, that's just going to work in the opposite manner. So we're going to decrease the concentration of H3O+, the equilibrium is going to shift to the right, and in doing so that's going to favour the production of hypochlorite ions. Remember what I said before, that hypochlorous acid is the key disinfecting agent, so this is rather undesirable, whereas this is desirable. Because there are two equilibrium processes at play here, what it means is that we need to manipulate the equilibrium through pH to try and maintain a high concentration of hypochlorous acid. In this graph here we can see that at a pH range of around 4 to 5, this is going to ensure that we essentially have 100% of the chlorine available as hypochlorous acid. As we increase the pH from this point, it will decrease the concentration of HOCl, but in doing so it will increase the concentration of hypochlorite ions. That's based on this equation here. Whereas if we were to further decrease the pH from a pH of 4, then that will decrease the hypochlorous acid concentration, but it will increase the concentration of chlorine, and that would be based on this equation here. So those effects can be summarized as shown here below. Before we talk about how hypochlorous acid acts as a disinfecting agent, we need to consider these hypochlorites because these are the active ingredients that we find in many bleaches and disinfectants. Sodium hypochlorite is typically what we call liquid chlorine because it's a soluble form, whereas calcium hypochlorite is typically called solid chlorine because it essentially is in a solid form. The benefit of bleaches and disinfectants consisting of sodium and calcium hypochlorite is that they react in water and they end up producing hypochlorous acid. We can see that in this equation down here. On this slide we can see the two different forms of hypochlorite. So granular pool chlorine here, we can see the active ingredient is calcium hypochlorite, and this White King disinfectant, we can see zoomed in that its active ingredient is sodium hypochlorite. So that would be in liquid form, whereas this would be in solid form. So the reason why hypochlorous acid, but also chlorine gas and hypochlorites, as well as other associated compounds, are classified as disinfecting agents is that they typically kill bacteria by their oxidizing action. In particular, they can cause the oxidation of proteins and enzymes within bacteria that are needed for their own growth. They could cause the denaturation of these proteins and enzymes, which would then render them ineffective, and then that would affect their ability to grow and reproduce. Out of these, we say that hypochlorous acid is the most effective disinfectant, and the reason for that is because it is an electrically neutral substance, and this means it can penetrate through the cell walls of bacteria. Bacterial cell walls are typically negatively charged, so we can see that hypochlorite ions would actually have a very hard time penetrating through the cell wall, so they would typically have to act on the outside, and eventually they can kill bacteria through this oxidizing action. To finish up, we can see how significant the difference in the ability for, say, hypochlorous acid and hypochlorite ions are in their oxidizing ability. This graph shows that it takes approximately 1.5 minutes for hypochlorous acid at a concentration of 0.1 parts per million to kill 99% of E. coli bacteria, whereas if we had a sample of hypochlorite ions at the same concentration, it would take 120 minutes to do exactly the same thing. And again, the reason for that is because the hypochlorite ions can only act on the outside of the bacterial cells, and so it'll take a really long time to essentially break down the cell wall and cell membrane, and then to affect their growth and reproduction. So that concludes our work on 4.2 water. Thanks for watching, and I'll see you guys next time.